Welcome! Today we are delving into the fascinating relationship between orbital periods and the semi-major axis. Using basic mathematics, we'll uncover the principle that governs celestial motion and explore the concept of eccentricity. Let's get started. Johannes Kepler, a German mathematician, astronomer, and astrologer, used simple mathematics to formulate three laws of planetary motion. According to Kepler's first law, law of ellipses, the shape of planets' orbits around the Sun is an ellipse with the Sun at one of the foci and nothing at the other focus. An ellipse is a plane curve surrounding two foci. In simple terms, instead of a perfect circle, an ellipse takes oval shape. In an ellipse, the sum of the distances from any points on the ellipse to each of the foci is a constant. That is to say, distance 1 plus distance 2 should be equal to distance 3 plus distance 4. Eccentricity is the terminology used to describe how flattened an ellipse or an orbit is. A perfect circle is not flattened at all, therefore its eccentricity is 0. When it begins to flatten, its eccentricity begins to approach 1. Eccentricity of any ellipse will be between 0 and 1 and is governed by the formula E equals to A divided by C, where E is the eccentricity, A is the semi-major axis, and C is the focal distance. Kepler's second law, law of equal areas. A line drawn from the Sun to a planet will sweep equal areas in equal intervals of time. The time it takes for a planet to move from position 1 to position 2, sweeping out area 1, is the same time it will take the same planet to move from position 3 to position 4, sweeping out area 2. Area 1 and area 2 are equal. This law also describes how the speed of the planet keeps on changing at different positions along the orbit. You will realize that the planet is fastest when it is closest to the Sun at the perigee, and it is slowest when it is farthest from the Sun at the epigee. Kepler's third law, law of harmonies. The square of a planet's orbital period is directly proportional to the length of its semi-major axis. The simplest way to represent this law mathematically is t squared equals to r cubed, where t is the orbital period of the planet and r the length of the semi-major axis of the planet. This law compares a planet's orbital period and the length of its semi-major axis to those of other planets. Thank you for watching and keep exploring Kepler's laws.